Our next chapter is on chemical bonding, so we're going to start off just talking about the basics of chemical bonding, why atoms form bonds. We'll talk about ionic bonding and covalent bonding and the distinction between the two and some of their properties, and then we will look at drawing Lewis diagrams. So to start, why do elements form bonds? Well, this bond formation occurs because elements are trying to either gain, lose, or share electrons in order to acquire a full octet. Now, octet refers to only the valence electrons. In row 1, which is what it's referring to here when it says n equals 1, so in row 1, that would only be hydrogen and helium. Their full octet is only 2 electrons, because there is only one orbital on that first row, and that's the 1s orbital. So those elements are trying to fill up that 1s orbital to be 1s2. Now we know that helium already has that, so hydrogen is trying to get 1s2 by gaining 1 electron, or hydrogen could lose 1 electron to empty its outer shell. In rows 2 through 7, so the whole rest of the periodic table, their octet is going to consist of 8 electrons. So these elements are trying to get a full s orbital, which we know holds 2, and a full p subshell, which we know holds 6 electrons, because there are 3 orbitals in that subshell. Remember, each orbital holds 2 electrons. Now there are some exceptions here to this 8, and we'll look at those. But for the most part, elements are gaining, losing, or sharing electrons in order to fill their octet. So that can be 2 if you're on the first row, or 8 on any subsequent rows. This slide is showing us the electron configuration that occurs when these elements form ions. Now to form an ion, we're going to gain or lose. What are they gaining or losing? Not protons, but electrons. For example, sodium. Sodium's most common ion is sodium plus 1. That means it lost 1 electron. So look at what happens when it does that. Here's sodium's original electron configuration. When it loses 1, it loses this outer energy level. It actually loses the whole 3s. So now it has 2 in the 2s and 6 in the 2p, and that equals 8, which is an octet. If we look at chlorine, chlorine's most common ion is chlorine -1, which means it's gained 1 electron. So it goes from 3p5 to 3p6. And if we look at that, that makes 3s2, 3p6 for a total of 8 valence electrons. So these two elements accomplish their octet in 2 different ways. Sodium is going to lose 1, so then it has a full outer shell when it gets rid of the 3rd energy level, and chlorine is going to gain 1 to fill that 3rd energy level. When these elements form ions, they're involved in ionic compounds. So ionic compounds are created when a metallic cation, with a cation, that's a positive charge, and those are from metals or hydrogen. But the cation forms an electrostatic bond with a nonmetal anion, and anions are negative. So your nonmetal is going to gain electrons, and the metal is going to lose electrons. And then the metal, which lost electrons, is going to be positive, and the nonmetal is going to be negative, and this electrostatic is talking about that attraction between these opposite electrical charges. So you have a positive electrical charge and negative electrical charge. The attraction between those two is what creates your ionic bond. To predict the charges that an atom will usually form, it's usually related to the group they're in. Now, a group is a column. And the reason that it's related to the column is because everyone in the same column has the same number of valence electrons. So, for example, in group 1A, this is just referring to what we would call group 1, their most common ion is +1 because all of those elements have one valence electron that they're going to lose. Group 2A, which is just what we would refer to as group 2, commonly +2. They have 2 valence electrons that they're going to lose. In the D block, that's our transition metals, and the F block as well, those elements can have a charge from 1 to 4, and it's really hard to predict what they are. When we move into group 3A, that's what we would call group 13 on the periodic table. So when they say 3A, talking about group 13, like where aluminum is, these elements are commonly +3 because they have 3 valence electrons to lose. Tellurium is a exception here, and it can be +1. In group 4A, which we would call group 14, like where carbon and those elements are, commonly +4, but tin and lead can also be +2. And the nonmetals in that group, they're going to form covalent bonds. So the nonmetals in group 14 really don't have a +4 charge or any charge for that matter. In group 15, these nonmetals are going to have a -3 charge because they have 5 valence electrons. So they're going to gain 3 electrons so that they then have 8 valence electrons. So in group 15, your nonmetals, since they have 5 valence electrons, they're going to try to gain 3 electrons. So that would give them a -3 charge and 8 valence, or an octet. But your metals in that group, the ones that are under the stairs, they could have a +3 charge or a +5 charge. So it's really variable, and you'll have to look at the situation to decide. In group 16, those have 6 valence electrons, and so they are going to want to gain 2. So they have a -2 charge. And then group 17, which is where our halogens are located, those are going to gain 1. They're right there by the noble gases, so they're going to gain 1 electron. That'll fill their octet and give them a -1 charge. So that's your basic charges. If you want to take your periodic table and put those charges at the top of the columns, that could be helpful as we're looking back. In the D block, those transition metals, they are going to lose electrons from their highest sublevel first. So this is key when you're thinking about the charge of these transition metals. Remember that when we write their electron configuration, so let's look down at iron. Iron's electron configuration is argon, then 4s2, 3d10. So when the electrons fill the orbitals, they go into the 4s first and then into the 3d. But when they lose the electrons, they actually lose them from this highest level first, which is the 4s. So if iron was +2, then it would lose those 4s electrons completely. So you see, as you move down, that they're not there. This happens with every single transition metal. That's why most of them like to have a +2 charge or something else, because having a +2 allows them to lose that highest level in the S sublevel. If iron makes a +3 charge, however, which is common, it would lose 1 of the 3D. And the reason it would want to do that, if you think about the setup of the 3D, you've got 5 orbitals. And then if you had 6 electrons, that'd be 1, 2, 3, 4, 5, 6. So iron would like to lose this one. See if I can get a different color here. This electron right here, because it's in sharing an orbital. So it's in a doubly occupied orbital, and so those electrons are easier to lose because the electron that's also in the orbital with it is also negatively charged. So that repulsion will help remove that electron. So iron can be +2 and get rid of the 4s, or it can be +3 and get rid of one of those 3D in addition to the 4s. Alright, so back to ionic bonding. You have your metals losing electrons, your nonmetals gaining them. So your metal is transferring electrons to your nonmetal. So then one of them is positive. Your metal is positive. And then your nonmetal is negative. And then you have that, here's that key term again, electrostatic attraction between them. Another way to say that is your cations from your metal and your anions from your nonmetals form an electrostatic bond based on their opposite charges. So the key word in either definition is electrostatic. You can talk about it as electrons moving from metal to nonmetal, or you can talk about it in terms of cations and anions attracting to each other. Remember that your cation or your anion could be a polyatomic ion. Here's just an illustration of how that might happen. So we have a sodium ion that has one valence electron, and a chloride ion, or actually it's just a chloride atom at this point, with 7 valence. The sodium will take its one valence electron and give it to the chlorine atom. So now chlorine has 8 valence, that's its octet, and that sodium lost its valence, so it just has those previous orbitals, which are already filled. The sodium will have a plus charge, the chlorine a minus, and that plus-minus attraction is what forms an ionic bond. So electrostatic attraction between the negative and positive charges. The strength of ionic bonds is dependent on what we call the lattice energy. And that's the value that you see down here for sodium chloride. Ionic bonds are very, very strong. So it takes a lot of energy to melt ionic compounds, or even more energy to vaporize them. We say that this process of melting or vaporizing ionic compounds is endothermic. That means you have to put a lot of energy in when you see that term. So what you see below is they're trying to take sodium chloride solid and turn it into a gas. And when you do that, those ions are going to split apart. So you're taking sodium chloride solid, where the positive and the negative, which aren't shown, are attracted to each other, and they're holding that together, and you're trying to split it apart. So you're breaking those electrostatic attractions. To do that requires some energy. Now for sodium chloride, it requires 788 kilojoules per mole. So if you had 2 moles of sodium chloride, it would require twice this amount of energy. Or if you had half a mole of sodium chloride that you wanted to vaporize, then it would require half as much energy. Different ionic compounds, though, are going to have different lattice energies depending on how strong their ionic bond is. So what factors affect the strength of this ionic bond? We know ionic bonds are strong, but some are stronger than others, of course. So there's 2 factors, and that comes back into Coulomb's law. Remember, we need to be very familiar with this law and its implications. So in an ionic bond, we have charged species. So we can use Coulomb's law. Okay, anytime you have 2, excuse my writing here, 2 charged, there's a C right there, charged species, then you can use Coulomb's law. So in an ionic bond, you have a cation, anion. So Coulomb's law comes into play. The force holding those 2 ions together is dependent on the distance between them and the charge on the ions. So if the distance increases, that's going to make the force decrease. But if the charges increase, then that would make the force increase. So we'll look at those 2 factors. And K is just a constant that you would use if you were actually doing the calculation. But we're just going to look at the comparisons. Okay, for example, which compound from each of these sets would have the greatest melting point and why? So melting point for an ionic compound is dependent on the strength of that ionic bond, because you've got to break the ionic bond in order to melt these substances. So for lithium fluoride and lithium iodide, the first thing you want to look at are those Q values. Okay, so think about Coulomb's law, Q1, Q2 over D squared. So think about charges first. So lithium's charge is +1, fluoride -1. Lithium +1, iodine -1. So the charges between these 2 are identical. So the charge is not really playing a role in one of them having a stronger bond than the other. What about the size or the distance between them? Lithium, for both of these, is going to be a fairly small cation. But what about fluoride compared to iodine? If we look at the periodic table, fluoride is near the top, so it's going to be pretty small, compared to iodine, which is going to be much larger. So if we think about distance, that's the distance between these ionic centers. So the distance in lithium fluoride is much shorter than the distance in lithium iodine. That greater distance, because distance is on the denominator, is going to create a weaker force. So lithium iodine would have a weaker force, so lithium fluoride would have a higher melting point. You got that reasoning? Okay, you might want to rewind and kind of listen to that again. But look at your charges first, and then look at the distance between the ions. Okay, so let's look at number 2. We have magnesium chloride versus magnesium oxide. The first thing we want to do is look at the charges. We know that magnesium has a +2 charge, +2. And we know that chloride, each chloride has a -1, while each oxide has a -2. Alright? Now when we're talking about charges, we're thinking about the absolute value of the charges, the magnitude of the charge. So for magnesium chloride, we have a Q of 2 and a Q of 1. Whereas magnesium oxide has a Q of 2 and another Q of 2. Both charges are 2. So magnesium oxide would have a stronger bond because the charges are greater. So after you look at the charges, if they are not the same, then you can base your decision solely on charge. You don't have to look at the distance because charge is the most important factor in Coulomb's law. Those charge values are going to be whole numbers, whereas the distance is a small decimal. Okay, so here the charge makes the difference. Magnesium oxide is stronger than magnesium chloride. All right, what about sodium fluoride compared to magnesium iodide? So in sodium, we have a +1, and in fluoride, we have a -1. So that's a 1 and a 1. In magnesium, we have a +2. Sorry, I can't make a 2 with my mouse today. And then in iodine, we have each one as a -1. So for sodium fluoride, we have a Q of 1 and 1, and in magnesium iodine, 2 and 1. 2 and 1 is greater charges than 1 and 1, so magnesium iodide would have a greater melting point, a stronger lattice energy, a stronger ionic bond. Alright, again, you'll see the explanations there out to the side if you want to jot those down or revisit those explanations. Alright, what about this picture here? Which of the following metal fluorides would have the highest melting point and why? Okay, well let's compare first of all. Let's see if we can tell the charges. We know they're fluorides, so we know that part's -1. Alright, now what about the metal charge? Well, let's check our ratios and see. The fluoride's going to be the larger blue, and I know that because it has the negative charge. So we've got, or actually, sorry about that, I think the fluorides are the red since they are the same in both pictures. Okay, so we have fluoride. In this A, we have 1, 2, 3, 4, 5, 6 fluorides, and 1, 2, 3, 4, 5, 6 metals. So if they're in a 1-to-1 ratio, then the metal must also have the same charge. Let's check over here. 1, 2, 3, 4, 5, 6 fluorides, 1, 2, 3, 4, 5, 6 metals. So that's a 1-to-1 ratio again, so the metal must also be +1. So they have the same charges in both pictures, but you notice the size is different. So in A, if we look at the distance between the ions versus B, the distance between the center of the ions, the distance in A is greater. So what does distance do to our attractive force? According to Coulomb's law, since that distance squared is in the denominator, the distance, the larger it is, the weaker the force. So that would make your melting point lower in A, because you have a weaker attractive force, whereas these in B, because they can pack in closer together, are going to have a stronger attractive force and a higher melting point. And there's your explanation written out again at the bottom. Alright, let's quickly run through the properties of ionic compounds. Ionic compounds are strong bonds, and the strength of those bonds is based on that Coulombic force of attraction. They have high melting points, they are very hard, and they have a low volatility. What that means, volatility is the ability of something to turn into a gas. And so these compounds do not turn into gases very easily, so their volatility is low. Whereas we would say a liquid like gasoline that you put in your car, that has a high volatility. It's changing into a gas, like an actual vapor, very easily. Another property of ionic compounds is they cleave along a plane. What that means is they're going to break along a plane, usually a fairly straight line. They have a very brittle 3D structure. So if you look at the 3D structure of an ionic compound, which you see down here to the left, you've got your negative and positives lining up in repetitive patterns. And this pattern maximizes the attractive force and minimizes the repulsive forces. So you can't really bend an ionic compound. It's not very malleable. You can't really stretch it into a wire. It's going to keep its shape because it needs to keep this arrangement. So if it is hit with something, that hit is going to shift off this line, this perfectly aligned ions. So if you look, you hit this ionic compound, oh no, now you have these two positives beside each other. That is going to cause repulsion and a cleaving along that plane. And so that is why ionic compounds are very, very brittle. If you hit a metal, for example, well, the metals will just move around. They're not going to break apart from one another, but ionic compounds, when you hit them, it creates a lot of repulsion, causing them to break off. Ionic compounds are mostly soluble in polar solvents, okay, and a perfect example of a polar solvent is water, but it can be anything that has a positive and negative area. But water is our favorite example. So when an ionic compound goes into water, it's going to break apart into its ions. For example, sodium chloride in water is actually going to break apart, so the sodium is separated from the chloride. The water will then surround the ions in very predictable ways. So if the ion is positive, this oxygen end of water will come around it. And if the ion is negative, then the hydrogen end of water will come around it. Because they break into ions in solution, they can then conduct electricity. So when an ionic compound is broken down either by melting or being dissolved, it will conduct electricity. Because now that you have charges, these charges are free to move, separate from one another, and they can conduct electricity. That's all electricity is moving charge. So when thinking, does something conduct electricity, think, can the charges move? If we look back at the ion in the solid form, so I'm going to slide back one slide. If you look at this ionic solid, these charges cannot move. So that is not a good conductor of electricity. But if you put that same compound in water where the ions are then free to move, it is a good conductor of electricity. The higher the concentration of those ions in solution, the higher the conductivity will be. All right, we'll stop there and pick up with covalent bonds on the next show.